So today topic is simple applications of refraction of light. We're starting today the third part of the chapter. How and where do we use this refraction of light and its concepts and its phenomena, and how they are helpful to us? That is the topic we're going to discuss today, right? So first of all, we should understand once again what refraction is, what refraction is, and how refraction works. And as such, we have done this before also. I just give you a little slight, refreshing of this topic. That what was actually the topic was. Okay, so the topic today is simple applications of refraction of light. I'm once again trying to discuss with you what is the refraction of light and how the refraction of light occurs and what happens when light is refracted. So we got a separation of two surfaces. We got this normal here. Assume that this is a rare medium and this is a denser medium, right? And assume also light is traveling from rare to denser medium. So how many of you know what happens now? So what happens is that whenever light travels from rare to denser medium, it has to change its velocity and it bends from its usual position, and it has to bend, say, towards normal.
What's a normal?
Light now
Normal.
travel like this, and this is what is telling us about the change in the right. Now this is rare medium, say air, and say it is water. So when I see through air and water, what I am finding is that light is changing. When you reciprocate the cases and you use the principle of visibility of path of light, then light suffers the opposite kind of refraction. It bends away from the normal. Angle of incidence becomes greater than angle of refraction. So this is the basic simple concept of refraction of light. So whenever there are two mediums, the two mediums of different densities, you always notice that light has to change. What it changes? It changes its velocity. It changes its changes the wavelength, the frequency remains the same. It changes the path. It bends towards the normal. It goes away from the normal. Something of that kind happens in the case of this path light is changed. This is the refraction basically. Light is traveling through two different densities of transparent medium. Light suffers two different refractions. Light passes through two different values, two different densities basically, and so light has to change. Now, this simple, please close your voice. Please close the voice, somebody. Now, this simple concept causes many kind of applications. Natural also, man-made also. We observe them in our life, throughout us, around us. There are many things in fact. Fine. So how do we so let us take few of them which are in our syllabus. There are many more, I will take them one by one. I'll send you them. I will send you more notes of this chapter as well. But right now, I'm taking 2, 3, which I will be discussing with you how light shows the change and what's the application of that refraction. The first one, which is most apparent around us, is a real depth and apparent depth. That whenever I'm taking a simple example. So whenever I'm cleaning it up, and I'm making a container containing some water, right? And say this is air over there. This is a water container, glass. You can say some denser medium than air, and an object is placed, and you place an object somewhere here. Say a coin, and it is at the bottom of the container right now. I mean, it's as simple as that, and you can see it through. And you can see that the coin is at the bottom, and this entire length is taken as its real depth. So here to here, it's a real depth, ch whatever. What you do is that is put some water into it. So what you have done is now you have placed some water. You put some water into it. As you put some water into it, now as soon as you put water into it, there is a change in medium. So there's change in medium, and there now this is all is air, right? This all is air, and this all is water. So I write down here that this is air and this is water. It is a denser medium. It is a rare medium. Who is not here? Ashwin Moga hai ya nahi hai?
Yes, sir.
Okay. A rare medium, it's a denser medium. Now imagine a light is traveling. So we should draw. So you want to observe this coin inside water now. You want to observe coin or object or some piece of pebble, whatever is lying at the bottom of the lake, of the pond, swimming pool, some pool of water inside, and you're observing that in standing in air. So where the observer is actually, observer is in air, and the coin, the pebble is in water. Pebble is in water. It's denser medium. You're observing the coin inside the water. You want to see where the coin is actually. What's the position of coin in the water? So I'm showing this ray diagram. You must all learn this. First of all, take a straight line and mark it as the normal. It's a straight line, a normal drawn from the coin. Light ray does not suffer any kind of refractions. It simply travels. I hope you all know that. Then there's one more oblique ray. Let us take an oblique ray. reaching the surface of water from the coin. As it reaches the surface of water, there is always a normal. I have told you many times by now. There is a normal, and I write normal there. This is angle of incidence. The incident ray. I think you are getting it all. Now what happens at this surface? Light suffers refraction from denser to rare medium. Denser to rare medium. Denser to rare.
Light will bend away from the normal.
Away from the normal.
Away from the normal.
From the normal.
We will bend away from the normal.
Light bends away from the normal. Light normal से away bent हो जाती है. Light has to change its path. All right. Are you understanding this point? And so I have got an angle of refraction in air. Light is going towards infinity. It's not intersecting any second light ray. I cannot find the image anywhere formed. So in such cases, you must be knowing it very clear. You know it very clear that light has to produce backward or forward to at least make an image. So what I do is that I'm making it a different color to make you understand that light is produced backward. Okay, it's not the actual light ray now. It is being produced backward. Please remember this point. And the object is being witnessed by the observer here. So what happens is that I am seeing the image of the coin here. So image is formed at this point instead of this point. So you can understand the point is that coin, I am not witnessing the coin at its actual position, rather it is at some shorter height than its actual height. Fine, say H2. And what is the real height? This is the real height. Say H1.
H1.
Say H1. This that you can see very carefully. So what happens is that and what is our concept behind this? Simple refraction of light from denser to rare medium. Light suffers refraction from denser to rare medium, and so light bends away from the normal. When produced backward, we find an image form slightly upward displaced than the actual position of the coin inside the denser medium only. So what is the point is that we always observe anything inside water. Now you say water, or you say any denser medium. Any denser medium. Light is inside any denser medium. We find that object is slightly upward displaced. Object is slightly upward displaced from its actual position. Light is slightly upward displaced from its actual position. And we see that, and this makes many applications. The pool appears shallow. The man standing in the pool, his legs appear shallow. You dip your hand inside the water, and you find the fingers are being shortened up. You dip a pencil inside the water container, you find the pencil is bent inside the water. All these are basically, the other thing is that means we are not observing the real object inside the denser medium. So write in the book somewhere, an important point, likhiye, write down, whenever an object is observed, you know, summers inside the denser medium, observer B in the rare medium object is virtual image of the object is witnessed, which is virtual, of course, and is formed slightly upward displaced, vertically upward. Please note this. Please note this point. So whenever we observe, so there are various versatile applications of this concept. I can again repeat, I mean, find in the book also. There is this also gave us a relationship between the refractive index of denser and rare medium. I told you that time, whenever things changes, whatever changes gives us the comparison between the refractive index of two medium, because it is because of the difference in the density of the two mediums that two such images are formed, which are slightly upward or downward displaced, which are not at their actual position. So I will discuss later on the factors affecting the displacement in the position of the object. That will tell us what is the relation between the refractive index of denser and rare medium in terms of the apparent and real depth. So right now, in this diagram, what I'm trying to tell you is that how the objects are slightly displaced upward and downward, and what are the various applications of this concept. And the condition important for that, as you can see, is that the observer should be in the rare medium. This you always please understand. Without this, we can't have this concept. So write down in the copy or somewhere, note down this point. It is necessary that light must travel from denser to rare medium for the occurrence of upward displacement. Note down, please. For the occurrence of upward displacement, light must travel from denser to rare medium. Because in the vice versa condition, this concept might not happen. You might not have this phenomenon when light travels from denser to rare. I will tell you later on what happens in that case. But right now you can write that whenever an object is observed by an observer being standing in the rare medium such that the object is in the denser medium, that the object is observed slightly upward displaced from its original position. So there are certain factors. I'll show the proving of this later on. There are certain factors which determines the upward shift. Which determines the upward shift actually. So I'm just saving it up and taking the next slide for you. So the first point for that the factors affecting how much the object is raised. How much objects are displaced
Factors affecting the upward displacement.
vertically. Don't speak in between. Displaced vertically upward. So I can give you, like I just told you, the first factor we should take care, we should notice is that it all depends upon the concept of refraction. Now we know this, denser the mediums or more the difference of densities of two mediums, or greater is the refractive index of the medium with respect to the first medium, more is the refraction, more is the bending of light. So here I would say more is the refractive index of the medium, greater is the difference of density of the two medium, more the denser medium is denser as compared to the rare medium, more is the upward displacement, more is the upward shift of the object. We'll find that we will find that object is displaced much and more, right? The first point, difference of the, I'm not writing the book points here. I should write down different points. You should make the things in your words. Don't try to cram the book. That is not required. Difference of the densities of two mediums. So if I say like more denser the medium is as compared to the lighter medium, don't mind the spelling mistakes here, lighter medium, more is the upward shift, more is the refraction, you can say. All these things are interconnected. More is the refraction, more is the upward shift, more is the difference. Okay, more is difference between the actual and the real, difference between, please keep on noting down somewhere in the copy or somewhere, actual position and the real positions, right? All right, I hope I'm getting clear to you one by one. The second point, the thickness of the medium. We can show this geometrically. We can show this geometrically that whenever we get more thickness of denser medium, more deeper the water surface, more deeper the water body, more deeper the glass object, more is the upward shift. The thickness of the medium, right? So it is directly proportional. They are directly proportional. Please note down this. They are directly proportional. So that means thicker the glass block. So have you ever observed, you put a glass block over a printed surface, no? And you find that printed objects seem slightly outward displaced, isn't it? So you put a glass block on a book or on some printed material, you'll find that object, you can see that printed material slightly upward displaced because now you are in air and the printed matter is behind or beside or immersed below the glass medium, which is denser, of course, than the air, and that causes those printed material to be upward displaced, which you can see now not at their own position but at slightly upward position. It is a simple application of refraction of light. So one point I'm adding to it, you notice that same medium, same glass prism, same denser medium provide different refractions, provide different refractive index for different wavelength of light. It provides maximum refractive index for the violet light of a shorter wavelength and provides lesser refractive index for the longer wavelength or red light or orange light and yellow light. Now, upward displacement is also corrected in that manner. So suppose you got 7 colors beside the glass block, you will notice that the violet color is maximum upward shifted because the violet has got shortest wavelength and maximum refractive index, and so the medium provides maximum refraction for that violet color and also maximum upward shift for the letter printed in the violet color, and it provides the least upward shift for the letter printed in the red color. There's a question later on in the exercise, we'll find out there. Least upward shift for the letter printed in the red color. It is because the light is actually following the upward shift also in the order of their wavelengths. You should write down in the book somewhere the third point. Actually, the third point is write down shorter the wavelength, shorter the wavelength. This is the third point rather. I write third point here. The third, shorter the wavelength of the refracted light ray, more is the upward shift. More is the upward shift in the denser medium. Okay, so the third point. So when we say shorter wavelength, that means in a spectrum going top to bottom, upward shift increases. Upward shift increases. So if they ask you to compare the upward shift of 3, 4, say red light and blue light and green light and orange light, so red will suffer the minimum deviation while the violet blue will suffer the maximum upward shift there. That is basically the concept behind, the upward shift through the mediums. That's how we discuss these things. So reading from the book, I am reading from the book now. Higher the refractive index of the medium, more the shift. Thicker the medium, more is the shift. the shift decreases with the increase in wavelength of light, or I have told you the shift increases with the decrease in the wavelength of light. So if I'm saying here, if I'm saying there that you got two wavelength, violet color and red color, so the upward shift will be more for the violet color and lesser for the red color. Why? Because red color has got the longer wavelength and the violet color has got the shorter wavelength. That is how the things works here. So if I say, if I add more things into it, more the frequency, lesser the wavelength, more is the upward shift, and less frequency, longer wavelength, red color, upward positioned colors in the spectrum, lesser shifted upward. So now the next topic would be, so I'll give you an example for that. I'll take it later on at what is that. But if suppose say, so our next topic should be how to find the formula for refractive index of a denser medium in terms of upward shift. So you must write in the copy, all of you. This meeting is about to be over. We'll take 10 minutes meeting more. After this, fine. So by that time, I'm discussing 3-4 points with you. So basically, I will prove it later on. Basically, the relationship between the apparent depth, the real depth, and the refractive index is that, say, if I take the previous slide again, say here it was air and glass. So tell me, what is the denser medium here? Glass is at what is the denser medium, and air is rare medium. Fine. So if I trying to find the denser medium refractive index, so I'm having A mu W. Now, A mu W is actually equal to real depth
On apparent depth.
upon apparent depth. Okay. What is A mu W? A mu W is the value of refractive index of water with respect to air. So denser medium ka refractive index with respect to air we're taking out, and it is actually equal to the real depth of the object inside the medium upon the apparent depth of the medium inside the water surface. So that is the actual relationship between, we'll prove it later on, actual relationship between the refractive index and the real depth and the apparent depth. There are certain points to interesting point we should remember here. Out of this, I'm taking the next slide again. So say suppose A mu G is 3/2. Now you all know this, we have discussed this before. Glass is a denser medium, so its absolute refractive index हमेशा 1 से greater होगा, and so it's 1.5 or 3/2. Now imagine there is a water body, water surface whose depth is say how much? 1 meter? Whose depth is suppose say 3 meters. Okay. And a coin is placed inside this. That means the coin has a depth of how much meters? 3 meters. All right. And A mu G is 3/2. Now we know this, that A mu G equals to real depth, real upon apparent depth. So I need to find out where would I be observing the coin inside the surf medium. कहाँ हमको coin दिखाई पड़ रहा होगा? Where we are observing the coin, how much depth we are observing it at. So I got 3/2 equal to 3 upon apparent depth. So apparent depth is 2 meters. That means there is a shift of
1 meter.
1 meter in the position of the coin. So you can understand that means the thickness of So if it is 3 by, so say I took water, say it's a glass also, you can say. It's basically, water is basically glass. I'm saying water is glass actually. So if ABGA is 3 by 2, therefore the thickness of glass lump appears only 2/3 of its real thickness when it is viewed from air. So you see what is happening. If I'm observing the glass symbol, this is a glass block. Observing a glass block, so tell me, the base of the glass block will be observed here, which is 1 meter above the base value, isn't it? This is only 2 meters. So what is the real depth? 3 meter.
3 meters.
And where we are finding it out? 2 meters. So so 2/3 of real depth पर हमको ये दिखाई पड़ रहा है. So the point is that whenever we observe say a glass block whose Ri is 3/2, it will only appears to us as 2/3 of its actual depth.